Are test corrections for test 2, or when do they do?
This one, before the end.
For the, okay.
Did you get
And I'll
that back, by the way?
Yes, you will. And apologies for not having them. It turned out I didn't have them at home. They were sitting in here. I had left them behind. Because I was panicking, I went through a stack of papers like 4 times and it still wasn't seeing it. And I thought, all right, where could it be? And I thought, did I leave it in the room?
I'm very grateful you didn't take the crummy teacher route and make us redo the test. Thank you for that.
Yeah, no, that,
Did people do that?
It's always at that point. It's
One
always-
teacher
Yeah.
who lost her work and made us redo it a long time ago.
I've had a teacher lose my work and make me redo it. I'm like, I'm not redoing it. I turned it in. This is stupid.
yeah. If it's an individual assignment that I've lost, in the past, what I've done is I just sort of make it go away.
It never
It doesn't
existed.
count for or against you. And if there was one class where I did lose all the quizzes, I did find them after the semester was over, but I did lose all the quizzes for one particular class years ago. And I think I just made that go away, it just, as if it never existed.
Did you tell them, or you just?
Yeah, no, I don't.
Oh, okay.
All right. So,
Can you make our quizzes go away?
not
The
yet.
only like test, this test 1B, if you can make that one go away, that'd be it.
Or no,
Yeah.
test 1A.
Test 1A, yeah, test 1A, test 1A.
Yes.
No, it was 1A, yeah.
Test
Yeah,
1A.
Keep 1B.
All right, so it's similar conceptually to the phasors, except this is an imaginary axis and this is a real axis. So as the phasors go around, in the phasor method, the instantaneous value is just the projection onto the x-axis. That's why it's cosine. So the projection onto the x-axis is the instantaneous value at that moment. And as they spin around, obviously, the values change. Here, we're going to treat it as imaginary and real, and it's the real part that would be the instantaneous value. So I can express this as the voltage from the resistor as the amplitude across the resistor times the cosine of omega t plus phi. All that looks exactly the same. That's ultimately the form we're going to put it in. I could also, instead of using cosine, I could do e to the I omega t plus phi. And I'm not going to go through the justification for that, but this is also, I could legitimately express it like this. But thinking about it this way does give me an advantage here of, if I'm multiplying vectors or phasors, well, I'm just going to end up adding exponents. Well, e to the I omega t is common to everything, but the phase here is going to change depending upon the phase shift is going to change depending upon the object. So I'm going to express this in sort of a polar form so v sub r I would express as just the magnitude and then the phasing. Because everything else is the same for everything else in the problem, for each of them. It's still cosine and then omega t is the same. All right, as we get into it, hopefully the advantage of this will become clear. So we still have the same setup, that has not changed. X sub c and omega, all of that preliminary information still is true. The difference is in how we're going to express what some sources will call the impedance. I looked up the definition of impedance, and some will just say the impedance is the relationship between the voltage from the power supply and the current, the ratio. But this one defines it a little bit differently, more specific to each individual one. And so I'm going to drop down to 1, but in the video I used the 2 hash marks to differentiate between Z for the entire circuit and the impedance for a specific circuit, a specific component.
Like just junction to junction?
Yes.
Okay.
Yeah. In a sense, no, it's not junction. It'd be junction to junction for those two, but not for this one.
Okay.
It's basically from one side of the component to the other.
Dr. Fox, if you have Like if it's truly EMF and it's ideal, is there no impedance?
There's still impedance because there's still resistance here. There's still, the ideal would be whether there's resistance in here or not.
Okay.
Oh, okay.
So Z sub R is just the rate, is not the radius, the resistance, the 150 ohms. Z sub C is negative J X sub C, or negative 106.1034 J. Now, J is, in this technique, is the square root of -1. I assume most of you are used to lowercase I being square root of -1, but we're using lowercase I for current, so it really might get confusing if I use I for two things in the same. We do that enough. So J, square root of -1. And for the inductor, is positive J, X sub L, so 125.66. J front or back, it doesn't really matter. So now when I'm adding these, well, if I can think of this as, I got a power supply here, I've got something here with Z is equal to J times 125.66. But that hit 2. So if I think about these like resistances, and I'm trying to find an equivalent resistance, well, first thing I'm gonna do is I'm gonna add the two that are in parallel. Well, I got something there, then I'll add something here that is in series with that, so I can come up with an equivalent resistance or an equivalent effective resistance. So I know that 1 over Z for RC, for that entire block there, is gonna be 1 over Z sub R plus 1 over Z sub C. So I'm treating them like resistors in terms of addition. That would be, and now I'm just going to go to 1 hash mark, just because I don't feel like writing 2. Get a common denominator. Therefore, ZRC is ZR ZC over ZR plus ZC. Now let's plug and chug. ZR, 150. ZC, negative J 106.1034 over ZR, which is 150, plus negative J 106.1034. This is the equivalent resistance or equivalent effective resistance for this bit right here. Now it's not a particularly convenient form, so we do need to, rationalize the denominator or whatever it's called. I guess it's not irrational. Multiply times the complex conjugate. So we're going to multiply top and bottom by the conjugate of this one, 150 plus J 106.1034. And on the bottom, well, I got I have binomials, A plus B, A minus B. So it's just going to be the first term squared plus the second, or minus the second term squared. Well, the second term is I'm going to have a negative J times a J, which is just 1. So my denominator becomes 150 squared plus 106.1034 squared. And the top is this times this times this, that would be my negative J, and then that times that to be my real part. If someone would be kind enough to multiply 150 times 106.1034 times 150.
23, wait. 2,300,087,326. I don't know, man.
Give me, all right,
2,387,326.5.
All right, and then that times 106.1034.
Sorry, would you point out again what we're multiplying?
So multiply these together and then distribute. So these times that should give us this.
Yep.
And then these times that will give us this number.
Okay, and that front number is gonna be 1688689.724. Cool.
So my denominator is,
Yes, what I got.
okay,
Denominator is 33,757.93.
all right, so I've got this binomial here divided by this, so I do the 1.7 million divided by this, and then the 2.4 million divided by that.
The first term is 50.02.
And the second is 70.72.
All right. So I have my equivalent resistance, or my impedance for this particular block here is equal to this. I'm going to leave it in this form for right now, because I want to figure out what is the equivalent when I add this into it. So I now have what this is, and I'm going to add that to it. In rectangular form is convenient. So I know that the total impedance is going to be that for the inductor plus that for my resistor capacitor block. So that is J times 125.66 plus 50.02 minus J 70.72. I got the real part.
50, the imaginary part is 54.94.
All right. So I now have my total impedance, as it is for the entire circuit. I know that the voltage from the power supply is equal to the current coming out of the power supply times my total impedance. So, voltage from the power supply. Well, I sort of need to establish some sort of standard here, so I'm just going to, in this case, start the power supply at 0 degrees. So this is 300, 0 radians is equal to I, the power supply, times that. Now, I have this in angular notation, or, in polar notation, and I have that in rectangular notation. So let's get them into the same notation. And so let's get this into polar notation. Remember, it's just like adding vectors. So the magnitude, 50.02 squared plus
94.
Okay, sorry, I was in the wrong spot there. 54 squared is going to be equal to my magnitude squared.
Dr. Fox?
Yep.
Why doesn't, I guess like at this point, why don't you include the imaginary and just make it 50.02 squared minus 54.94 squared?
Because that's real and imaginary, and so it looks like that. The magnitude of this,
Oh,
imaginary's sort of built into that.
Well, back to 74.299.
What do you get again?
74.299.
74.299, okay, that's equal to Z. And my angle, well, I go over 50 and up 54.94, they are both positive, right? Yeah. So if that's 50.02, and that's 54.94, that angle is the arctan of 54.94 over 50.02.
in radians, I got the angle as 0.8322.
Yep. Therefore, let's get rid of some stuff. Oop, that did not click. Oh,
It looks nice.
all right. So I have 300 at 0 radians is equal to IPS times my Z, which is 74.299 at an angle of 0.8322. So for IPS, I just divide both sides by this, the 74.299.8322. So 300 divided by 74.299
4.037.
amperes, because it's current. And an angle, this is where this is convenient. I just subtract.
Okay, that's what I was thinking.
Negative 0.8322.
Oh, so when you have the division, you just subtract the
Yep.
top angle from the bottom angle?
So current from the power supply, 4.0372 amperes and negative 0.832.
2.
That's the same current as is flowing across my inductor. 4.0372 and negative 0.8322. I know that the current flowing into IRC has to be the same, because it's going out of the power supply across the inductor, and then it comes into this mess right here. Oh, okay. So I can now find the voltage from the power supply. I know that the voltage, sorry, using just words randomly apparently, the voltage going into my parallel structure has to be the current going into the parallel structure times the impedance of the parallel structure. Well, the current into the parallel structure, we just found that, that's 4.037 at an angle of negative 0.8322. Z, we had calculated before, but I have erased. What was my Z over C?
Like CRC. Like it's either, is it the 150 or the 106.34? 34.
No, it was the combined, after we added them. We did the reciprocal, the sum of the reciprocals.
54 point,
So 50.02,
Plus 54.94J. Is that right?
got a big finger. No, that was the 70, there was 70 in there.
oh, so it's
No, that
50
was after we added,
Is this the 125 minus the 70?
Yeah, is it that one? Or 50.02 minus
because we,
J70.72?
minus, was it minus J and then 70 point something?
72, yeah.
70.72?
Yeah,
Okay.
that looks right.
Let's get it in polar form, because it's gonna be a whole lot easier to multiply it that way. So my magnitude, 50.02 squared plus 70.72 squared. Equals ZRC squared. And then my angle is going to be the arctan of negative 70.72 over 50.22.
Negative 0.9552?
The angle,
Yes,
negative 0.9552. Is that what you said?
I hope. That is what I said. I hope that's the angle.
It's close to what I had.
Good.
And then ZRC,
86.62.
alright, so 86.62, an angle of negative 0.9552. Multiply them, you multiply these together.
And then you would add angles together?
Yep. And so we get the voltage across R and C.
That is 4.037, correct?
Yes.
Okay.
It's 349.69.
And an angle of
Negative 1.7874.
so we now have